All right, another installment of me talking at my iPad, and hopefully you guys watching. This is gonna be a review of energy, not just energy, work, energy, and power. All right, so if we start off, usually the first thing we talk about is work, and there's two definitions of work. One is a pretty simple formula. It's pretty simple if I could write it the right way. The work is equal to the force times the distance. Second definition of work is the transfer or transformation of energy. So when energy goes from, let's say, from potential to kinetic or vice versa, work is being done. If you have no energy and you say, let's lift this mass up in the air, you're doing work on it. The work that you're doing, that F times D, if this is distance D and you're applying some force to it, is going to transfer energy to it. And I hope you guys know that it turns into potential energy. And there's two types of potential. One is gravitational, and we're doing work against gravity, so this is gravitational potential energy. All right, so while we're talking about energy, the big idea there is it's conserved. And conserved means it's neither created nor destroyed. For our purposes, really what that's going to mean is it's just going to be transferred between different forms. It might go from potential gravitational to kinetic. Some of it might turn into internal energy or heat. Internal energy or heat. So what would be an example of this? So let's say you have a ball that you're on top of the roof that you drop. It starts with gravitational potential energy. As it starts to fall, you still have gravitational potential energy because you're still at some height, right? But you also have kinetic energy because it's now moving. Now, if we remember our formulas, this one's mgh, this one is 1/2 mv squared. And then when it reaches the bottom here, it's going to have a height of 0, so it won't have any potential. It'll be all kinetic. But let's say this number does not match this number. You might ask yourself, how can they not be equal? Real world, there's friction. In this case, the friction is air resistance, and that friction causes this internal energy. So if we started at the top, we'd have PE at the top, and at the bottom we'd have some KE, and we'd also have some internal energy. A lot of times we write internal energy as just Q. Okay, so that would explain, why is this not equal to that? Now, some of you guys confuse, like you think when it hits here and it stops, now it has no kinetic energy, no potential energy. Energy is not conserved all of a sudden, it's destroyed. Well, what's going to happen and what you don't notice necessarily, it's not a visual thing, is when it hits the ground, there's sound, which is a form of energy, and those sound waves will travel outward, which we'll learn about hopefully before the end of the year. And also the ball would get a little bit hotter, and that, I guess heat is a better way to write it than hot. Heat is another form of energy. So this thing is red hot now because it hit the ground. No, it's not red hot, but yeah, that's where some of the energy would go. All right. What we call PE and KE is the mechanical energy. We call it total mechanical energy. And if there's no friction, that's always going to stay the same. So what that means is if I sort of had two bar graphs of PE and KE, as this one went up, this one would go down, and vice versa. So let's say this one goes up, this one would have to go down. If you summed the two of them, this would be your total mechanical energy. That would stay the same. All right. A second form of potential energy that I kind of got away from, we had PEG. Now we have PE of a spring or PE elastic. And to do this, we have to start out with a law. I'm going to put it in quotes. It's not a capital L law, it's a little l law. And that's F equals kx. It's known as Hooke's law. And what Hooke's law says is that the force on a spring is proportional to the stretch on the spring, which kind of makes sense. The more I keep stretching this, the greater the force is. And the slope of this is what K is. And you can imagine that the stiffer the slope, or excuse me, the steeper the slope, the stiffer the spring. And I hope that makes sense, because that means for a small amount of stretch, it takes a lot of force. Whereas if you had a really shallow one, this would be stretchy. And for a lot of stretch way out to here, it doesn't take much force. So this would be like a rubber band, and this would be, something like a metal. Okay, a really thick spring, maybe like a car spring versus a clicky pen spring. Okay, so that's Hooke's law, and the spring constant is K. That's the slope. That's this thing right here. So that basically tells you how stiff the spring is. Okay, what we use that for is to calculate how much energy there is in a spring. It's 1/2 kx squared. Okay, so that's where the spring constant comes in. Well, that's pretty much it in my brief review of energy. So again, we were supposed to learn this the first time around, so I'm going kind of fast. But I hope this is, again, knocking those cobwebs loose and helps you guys to remember some of this information. Like always, I'm going to attach a CASEL Learning, or not attach it, but I'll assign it, and make sure you're working on that when you get done watching this video. Thanks for watching.